Hi and welcome to Unit 1, Topic 3, Video 15. And in this video, we're going to look at two more further geometric proofs examples using vectors. So I really like this example too, because it's something that usually, a lot of the math questions you get in vectors, you look at it and go, well, it's just obvious, and then you've got to prove it. And proving something that's obvious is annoying. But often with this one, people look at it and go, well, it looks obvious in the diagram, but I reckon I could draw a shape where it's not true. And so it's really cool that actually you can prove that it is always true. So the question says, prove using vectors that for any quadrilateral that when any two pairs of adjacent midpoints are connected, they form two vectors that are parallel and equal in length. So we're talking about midpoints here, 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 and here. And if you connect them, and it would be the same as if I connected these two, that they are equal in length and parallel, i.e. they are equivalent vectors. That's what we're trying to prove, equivalency. Okay, so let's start this process, and the easiest way to start this process is to do some definitions. So I'm going to build a bit of a profile of our shape. I'll start with A, B, C, D, and then E, F, G, H. So that seems like the easiest way to define things, but I'm going to also define using just simpler vector terms. So I'm going to call this, in fact, I'm going to go with the small ones for this. I'm going to call this X and Y, and then this one W, and this one Z. So we use up X and Y, and then we have to go either side. But I'm going to call the midpoint to the edge W. So keep in mind this is a midpoint though, so this is W. This is Y, this is X, and this is Z. We know that to be true. Okay, so let's go through and do some definitions of key information. EF is equal to X plus Y. Hopefully you can see that. And we want to show that it's equivalent to GH. So GH, that's going to be funny. Well, that's equal to, not GH, sorry, HG from bottom to top. Now, HG, unfortunately, to get from H to G, I've got to work backwards here. So H to G is Z plus W, except they're both negative because I had to work backwards. So that's the information I've got, and I'm going to try and prove from that situation. The other relationship I've got, which might not be as obvious, and this is where it becomes interesting, if I start at A and I work my way around, AB plus BC plus CD plus DA. Okay, now remember this is kind of like a displacement situation. That's equal to 0. I'm starting and finishing in the same place, so I've actually gained nothing. The vector is just 0. Now I also know that AB is equal to 2x, and BC is equal to 2y, and CD is equal to 2w, and DA is equal to 2z. And that's equal to 0. And so now I can divide by 2. I can say x plus y plus w plus z equals 0. And then I can subtract w and z, and I get x plus y equals negative w minus z. Now x plus y is EF, and HG is negative w minus z, or negative z minus w. And so I've proven they're equal. They're equivalent vectors. They're exactly the same. And that proof is fairly simple, but it proves something that might not actually seem that obvious, but you draw any quadrilateral at all, and this will be true. Okay, so that's example 2. Let's have a look at example 3. You might want to pause and have a read of this now, or listen to me read it. The position vectors of points A and B are A and B relative to the origin. So we're calling them vector A and vector B. So I might actually draw this. Now I'll start drawing it now. So let's start with our O. O is here, and O goes out to C. But we have A on here. Now I've read ahead a little bit, so I'm cheating. And then we have this vector here, which goes out to B. And this is vector A, and this is vector B here. Now the question says, line segment OA is produced to C. So when we say produced, it means it's extended. So C is here. So that OC equals MOA, and that means that OC is parallel to OA, and it's M bigger. And now we know, I'll make this note here, M is greater than 1. May or may not be important, but it's produced. C is joined to D, which is the midpoint of OB. So D is here, and there is absolutely nothing telling me this is a right angle. So my diagram already has got a couple of little problems. So I just need to be aware of that and wary of that to make sure that I don't muck that up too much. And don't assume parallel. So D, which is the midpoint of OB, which means that this is a half B, and this is a half B, which may or may not be important. E is the point on CD such that C equals NCD. So E is here, and I'm deliberately choosing this point because I'm reading ahead. So that's our E, and CE equals NCD, which means that N is less than 1 because E is on CD, it's not a produced point. Determine OE in terms of A, B, M, and M, and if A, E, and B are collinear, find M's in terms of N. So here's my little extra line, which I do in green. We're saying they're collinear, which we'll come back to a little bit later. So let's start with our answer to A. Determine OE in terms of A, B, M, and N. So let's start by saying how we're going to get from O to E. And I can see two ways of doing it. I can either go up here and then down. That's based on information I know. Or I could go out here, or actually no, I could go to there and up. I don't know anything about that green line, so I'm going to be wary of using that green line. Although, oh, no, I do know a lot about the green line because the green line is just AB, which is minus A plus B. So I could use the green line as well. There's three ways of getting to that. So what I'm going to do is I'm going to use my first option, which is OC plus CE. So here's how I set it out. I want to work out vector OE, and I'm going to say it's equal to OC plus CE. Okay, so that's how I get from O to E. Now, moving forward, I know something about CE. So let's make that note. CE is equal to NCD. So that's important. And moving forward again, I know stuff about CD. CD is equal to CO plus OD. So I'm going to use that information because I know CO and OD. So CD is equal to M, well, it's just a negative because I'm working backwards, MOA plus half B, and OA is just A. So negative MA plus half B. And so therefore, CE is equal to N times negative MA plus half B. Okay, so we're somewhere. Now, we've made a statement about OC, which helps us as well. And so I'll make that little note over here. OC is equal to MA, because I've got an OC in my original one and a CE. And now I know about CE and OC. And so I can say, therefore, OE is equal to MA, which is my OC, plus N times MA, except that's negative, plus a half B. And that's going to be equal to MA minus MNA plus a half B. And to write it fully in vector form, I get M minus MN A plus a half B. So here's the value of my OC. Oh, I've got a little bit of an error here though. Of course, when I expand that bucket out, the n does go in there as well. So if you picked that up while I was doing the video, I apologise. So I'm just going to add that in there. It's always good to be thinking and considering whether you've made mistakes along the way as well. So there's my value of OE in terms of A, B, M and N. Now, like I said, there's plenty of ways to go about getting from O to E, and the way you choose should give you the same simplified version. So if you want to, go ahead and do it a different way now and see what happens. It should give you the same simplified version every time. The issue is that if you go, in particular, if you go along our third option here, we won't get M's and N's. And the question has asked us to do it in terms of M's and N's. So we've got to be careful that we make the right choices. If I go from O to D and up to E, I'll get M's, but I won't get N's. So there's some issues there in terms of making selections that match what we're trying to find. And we need it in terms of M, which means we really need to use OC. If A, E and B are collinear, find M in terms of N. So we know A, E and B are collinear. And so that means a few things. That means that we could work out AE and AB and then use that collinearity and the fact that we use OE to get AE to look at the coefficients. And so that's the plan that I'm going to take in doing this solution. So we've lost the diagram. In fact, we have lost the diagram. So what I'm going to do is I'm going to take a copy of the diagram to help us. That was silly. I'll put the diagram down here, and so you can still see the diagram as I do part B. So part B, I know because I'm told they're collinear that AE is equal to K times, well actually I'll write this out, AE is parallel to AB, and so therefore AE is equal to KAB. It's always good to show all the evidence you've got. And we also know that AE is equal to AO, so I've zoomed in so now we can't see the diagram, there we go, AO plus OE. And that's equal to negative A because we're going backwards, plus M minus NM A plus half NB. Okay, so we've got that information. Now I'm going to factorise that AN. That's equal to M minus NM minus 1 A plus half NB. And we know that's equal to K times AB. So now I'm going to use that K times AB and recognise that AB is equal to K times, how do we get from A to B? We go AO plus OB, and so that's equal to K times negative A plus B, negative K A plus KB. Now this is problematic because I've introduced K now, and I'm asked to find M in terms of N. That's the key. So I want to find M equals something in terms of N, nothing else. So how am I going to eliminate the K? That's our problem. Well, this is what happens now. We've got our, remember our M, remember our all up here. If I go right back up to an early video, this rule. If MA equals plus NB equals PA plus QB, then M equals P and N equals Q. So we'll go down different M's and N's, by the way. We'll go back down to here. And this implies that, firstly, that is equal to that. So I get negative K is equal to M minus NM minus 1. And I'll call that number 1. And it implies that this equals this. And so I get K equals a half N. And I'm going to substitute 2 into 1. And it gives me negative a half N equals M minus NM minus 1. Now, I'm not a big fan of halves, so I'm going to double everything. I get negative N equals M 2M minus 2NM minus 2. And I need to get m by itself, so I'm going to swap sides first of all. Just makes my life a bit easier. And then I'm going to start rearranging to get m by itself. So I'm going to add 2 to start with. 2 minus n. Then I'm going to factorise out the m. And then I'm going to divide through. And there's my answer. M is equal to 2 minus n over 2 minus 2n. So whatever n is, m is equal to that. And we could use that, if you knew n or you knew m, you could use that to determine the other. So there's our second example. You ask for very specific things. It's not so much proving things that we know to be true about quadrilaterals, for example. If you go into your textbook, you'll find examples of how to prove that parallelograms have diagonals that bisect or whatever it is. But here's one that might come up. It's quite a hard question, and the type of thing that might come up where you've got to play with some unusual situations. So have a watch this video again if you need to. Maybe in a couple of weeks, come back and try and do the question yourself without watching the solution again. All the best.